Greetings there, Pythonistas, YouTubeistas, and so on. This is kind of an addendum to a previous set of two videos where I started in Codesters. I'm not going to even look at Codesters in this one. I jumped us into a more, I'd say, adult development environment called Spider, VS Code, PyCharm. There's a list. The big thing in IDEs is interactive development environments. Are they designed? I mean, this can be a big thing. Here's one choice you can make. Are you looking for an IDE that's all customized, geared for a specific computer language, or do you want the kind of IDE that through use of plugins and various add-ons, you're able to jump from one language to another easily? Because a lot of us were working in a multi-language situation, right? There's Go in one section, and there's JavaScript over there, and there's Python over there. Maybe we added Python late in the game, but it was easy enough to add, but we already had three other things going, that kind of thing. So I'm going to assume kind of a polyglot atmosphere when it comes to who's using this stuff. It's not like I know everybody in the Python community. I know one or two, three, four, five. I'm a very finite kind of person, but over the years I've developed an impression from meeting a lot of people at PyCons and EuroPython. I've been to some of those. Anyway, I'm giving you kind of an average profile of the Python user, and I'm saying so many of them are not just Python programmers. They program in many other languages as well. So where I kind of left it actually was with the virus, right? I'd done a web search on the virus shape, and I was talking about polyhedral numbers, the icosahedral and cuboctahedral numbers. Let's go straight to that, the online encyclopedia of integer sequences, and pull up what I'm talking about when I say icosahedral numbers. Remember, we were looking at pictures of viruses. Now, I'll just refer you to the previous video and where it left off. See, when I make these videos, I link them together in different ways. Like in a blog post, they'll be like part 1, part 2, part 3, or this is a sequence. But then really, I made them in a different order originally and stuff. You can rematch these. So there's the sequence, 1, 12, 42, 92, and look how it says cuboctahedron or icosahedron, right? So that's the kind of numbering I'm interested in connection with the cuboctahedron and the icosahedron in particular. And that's a cuboctahedron there on the outside in the yellow. Now, what I wanted to reassure people in this addendum is, I was talking about a very, very simple polyhedron class that didn't seem to know how to do anything except to numerically adjust its own volume and edge length. Like you choose something, you'll call its edge length, right, of a polyhedron. Think of a cube. And then you say, okay, I want all those edges to be bigger by the golden ratio, like 1.618. So zap them all bigger by more than 150%. And so what happens to volume? Well, it changes as a third power of the change in edge length. So when I create a tetrahedron subclass of polyhedron, all I'm doing is anchoring a few numbers, edge, volume, and then how many topological features in terms of edges, vertexes, and faces. So that initializes, gives birth to a tetrahedron. And then there is no other code for the tetrahedron in this example. It's all inherited through polyhedron, right? So in Python, we say the parent class, and then we put the parentheses here. So we're going up the ladder, you could say, to the top class. Now there is a class above this. You could call it object. We don't have to explicitly inherit from. But here at polyhedron, at this level, are all of our special names other than init, which is giving birth to. This is less than, greater than, equal to. So I'm defining the protocol, what should happen with the use of, say, a greater than sign vis-a-vis another polyhedron. I can compare them, and I can get true, false, basically. So same with cube and so forth. We've got the root of 2 for an edge on my cube, if you've watched my other videos, but the volume is 3. And that's kind of strange. That's where you have to say, oh, well, there's something else going on here. And I can take you through those videos in a different sequence where we talk about the quote-unquote Martian math paradigm. But what I really want to reassure you of in this particular video is that, yes, the guts of your polyhedron you could flesh out with whatever code you need to actually start to render these things as graphical objects in your Jupyter Notebook, like with Visual Python. Or you can, what I've done often is, like when VRML was big, I wrote out to VRML from inside of Python or another language. I would write the necessary script for this particular object. Like, I'm a tetrahedron, I need to render myself somewhere. What should I do? Well, you store in a method in your tetrahedron the way to write out a chunk of code in another language, basically. Scene description language for POV array is still a viable, very viable way to go. And at my Oregon Curriculum Network online, I have a page of Python plus POV array is important in that website. I think to this day it's as relevant, if not more relevant than ever. A lot of my stuff's written in Python 2. It's not that different, so it's all there to be adapted. Just, copy the whole website. Use wget on it, something like that. All right, so that's what I wanted to reassure you of, is that actually all our vectors and vector calculations come in here, and I actually recommend looking at such things as my Python 5 subfolder in my 4D solutions on GitHub. This is where I've got a lot of this stuff already there for your benefit. For example, let's talk about just the stem. Let's see, where's the stem math? So you'll see this long list of stuff, right? And what's fun is when we get into actually rendering these polyhedrons, I don't just stick to the XYZ coordinate system. I throw in another more esoteric coordinate system as grist for the mill. It helps you chomp on the jargon of linear algebra, say, if you have another, not polar coordinates or spherical coordinates, those are in the mix as well. I'm talking about quadray coordinates. Turns out that in quadrays, I can give positive whole number integer coordinates to each of these spheres quite easily, which makes them database well and so forth. Now, these are the cuboctahedral numbers, you could say, in sequence. Let's see if I can time my voice right. So it's going to be 1, 12, 42, 92, 162, and so on. It just keeps coming outward, and this is the number sequence here, 92, 252, 362, 492, and you can also accumulate those. You can accumulate those numbers, and this is where I like to go. Let's see, is this where I like to go? Yeah, I like to go to my own name here. You could say it's my vanity plate, but it does take us back to the virus story. So I'm going to end there, kind of where I ended the last one, and recap that my addendum here is designed to reassure people who see my very slim polyhedron code that I'm not abandoning the idea of representation like computer graphics, and you can do a whole vector class under this and have that take over when it's time to actually show these things. That's called Stickworks in my library. Okay, I wrote something simple for that. But you can write your own kind of, roll your own in this department as much as you like, obviously. Just keep it simple if you just want to talk about volumes and the topology of these things, though. Like, I can see a stripped down like this style working for a bunch of classes because you're not always interested in the whole mechanics of rendering on screen and so forth. All right, talk to you again. Have a great day.